Hi everyone, my name is Sunbeom from Korea University. In this presentation, I will talk about our recent work on automatically finding vulnerabilities in smart contracts. This is co-work with Seongjoon and Hakjoo. Smart contracts are digital contracts written in programming languages. Smart contracts can be useful in various domains such as decentralized finance or food supply chain. Users of smart contracts can send transactions by invoking functions. For example, consider the transfer function implemented in Solidity language. As shown in the slide, using this function, a user X can send some tokens by invoking the transfer function and providing proper argument values. For two main reasons, ensuring safety of smart contracts is a critically important issue. First, since smart contracts are immutable, bugs in smart contracts cannot be mitigated once smart contracts are deployed on the blockchain. Second, smart contracts typically manipulate valuable data such as digital assets. Therefore, even a single glitch can cause tremendous financial damage. Indeed, due to flaws in smart contracts, there have been many large-scale accidents that caused huge financial damage. To mitigate safety issues in smart contracts, we propose a new technique for analyzing safety of smart contracts. Specifically, our goal is to find vulnerabilities with concrete scenarios in terms of transaction sequences. I will explain our goal with a concrete example. In this example, the line 30 has an integer underflow vulnerability. However, even though the vulnerability is reported by analyzers, it would not be easy to understand how the bug can happen. For example, as shown in the slide, simply sending a single transaction after the deployment will fail to trigger the underflow. This is because all elements of mapping variables are initially zeros. Therefore, when invoking one from function, if a positive number is given to the second parameter, the guard expressions at line 26 and 27 evaluate to false. To trigger the underflow at line 30, as shown in the slide, we need a transaction sequence of length 4. As we demonstrated, in addition to merely pointing out vulnerable locations in a contract, we aim to effectively find vulnerable transaction sequences that can demonstrate the flaws. Finding vulnerable sequences is crucial for practical smart contract analysis. Without sequence information, developers should manually inspect to decide whether reported warnings are true positives or not. This manual investigation is time-consuming and error-prone. The technical challenge is that the number of possible combinations of transaction sequences is interactively large. Unfortunately, suffering from this challenge, existing symbolic execution techniques often fail to find vulnerabilities that require long transaction sequences to be found. In this work, to effectively find vulnerable transaction sequences in smart contracts, we propose a new symbolic execution technique called SmarTest. The key idea of SmarTest is to guide symbolic execution with the language models towards paths that are likely to contain vulnerabilities. Specifically, in the training phase, we perform unguided symbolic execution over training contracts. Then, we collect vulnerable transaction sequences from the contracts and learn a probability distribution over the vulnerable sequences. In the testing phase, the symbolic execution guided by a learned model can effectively find vulnerabilities for new contracts by prioritizing sequences that are likely to be vulnerable. Now, I will talk about technical details of learning and testing phases of SmarTest. In our work, we use the Ngram language model. In Ngram models, the probabilities can be computed by using Ngram counts. Therefore, the goal of the learning phase is to construct a training corpus where we can obtain n-gram counts from it. The issue is that how to abstract transaction sequences for effectively generalizing to unseen new contracts. In the context of Solidity smart contracts, our idea is to use type information. We use this idea because we found that type information is important for characterizing behaviors of functions in Solidity smart contracts. For example, given a transaction that invokes setOwner function, which designates a new owner of a contract, we can abstract it to a feature vector that sets the third and the sixth element to 1, which means that a variable that has address type is defined and used in the transaction. With this abstraction method, now we can construct a training corpus by abstracting all of the obtained transaction sequences. Now, I will explain the testing phase. Suppose we have a transaction sequence. First, we abstract it to a word sequence in a similar way to the one in the learning phase. Then, using the training corpus that we obtained, we compute the probability of being vulnerable for the given transaction sequence. Finally, according to the computed probabilities, we prioritize the transaction sequences to guide a symbolic execution procedure. Now, I will present experimental results. We collected benchmarks with known vulnerabilities from public datasets, such as CV-reported contracts. When necessary, we constructed our own benchmarks. We compared SmarTest with 5 recently developed analyzers that can generate vulnerable sequences. We used the trigram language model, which was effective enough in our experience. To evaluate the robustness of the models, we performed 4-fold cross-validation. As shown in Table 1 and Table 2, we found that SmarTest consistently outperformed 5 tools in terms of vulnerability finding ability. For example, in terms of finding non-CV vulnerabilities, SmarTest found about 90% out of the sampled CV reports. By contrast, Visceral and Manticore collectively found about 35%. In our experiments, we found that using language models significantly improves the performance of symbolic execution. For example, for the CV dataset, SmarTest without language model took about 30 minutes to find about 2,200 sequences. In contrast, SmarTest with the language model took only about 1 minute to find the same number of vulnerable sequences. We also observed a similar trend for the leaking suicidal dataset. Finally, using SmarTest, we found 7 critical zero-day vulnerabilities from the wild contracts which violate the ERC20 standard. We categorized them into 2 patterns. The first pattern is a case where any user can have tokens for free due to mistakenly named constructors. In older versions of Solidity, a function whose name equals the name of a contract is a constructor function. Here, since the names are different, bToken is not a constructor function. As a result, bToken function can be invoked by anyone at any time, allowing anyone to have tokens for free. Based on the comment at line 2, we conjecture that the developers mistakenly named the function. The second pattern is a case where unauthorized users can send the tokens without restrictions. Specifically, in ERC20 token contracts, the transfer from function should be invoked by authorized users. However, since the red colored part is absent in the original code, unauthorized users can transfer tokens without any restrictions. To summarize my talk, I presented a new symbolic execution technique for smart contracts. Specifically, our goal is to effectively find vulnerable transaction sequences in smart contracts, which is crucial for practical smart contract analysis. The key idea is to guide a symbolic execution procedure with the language models towards passes that are likely to be vulnerable. The implementation of SmarTest and the benchmarks that we used are publicly available. Thank you for watching this video.